In this topic we're going to look at mathematical similarity. We're familiar already with the word similarity or similar, and in the English language obviously it means two things are roughly the same to some degree. When we talk about things being mathematically similar, the conditions that need to be met for things to be mathematically similar, the conditions there are much more strict, and we're generally talking about geometrical shapes. The two conditions that need to be met for things to be mathematically similar are: one, corresponding angles must be equal to each other, and two, corresponding sides are in the same ratio. And we can now have a look at what that means. What I have here is two shapes which are mathematically similar, so just how would I show that? So starting off with our first condition, corresponding angles are equal, we would need to decide which angles correspond to each other between these two shapes. So for instance, this angle here would correspond to this angle here, in that they're in the similar position in these shapes. So we could maybe put a little cross in here to represent that. And those two angles, if I was to measure them, they would be exactly the same number of degrees. Similarly, I can go through and right round this shape and work out where all my corresponding angles are. So maybe a little circle there, a little circle there. Those two angles again, if I was to measure them, they would be identical. In other words, corresponding angles there are equal. With the bottom corner here, the sharp corner, use a little triangle. These are identical. And lastly, we'll use the little arc here to represent this. In each case, what I've marked out there, the corresponding angles on each shape are equal to each other. We'll now look at the second condition, which is corresponding sides are in the same ratio. First of all, before we can do this, we need to identify the sides on each shape which correspond to each other. So, for instance, these sides that I'm marking off in yellow are corresponding to each other. In other words, they match up on the smaller and the larger shape. And we can go through all of the different sides and match them up with their corresponding sides. So on the larger shape, the side I'm highlighting in pink would correspond to this side here. The side that I'm marking off with blue on the larger shape will correspond to this side here. And we'll use green for our last one. This short side up at the top here will correspond to this short side up here. Now if I take these colours, red, blue, green and yellow, and start to look at the ratios, starting off with the kind of red or pink side here. So the ratio of the sides there is, on the larger shape, that pink side is 16 and to 8. If I was to simplify that, that simplifies down to 2 to 1. For the blue sides, the ratio is 12. And on the smaller shape, the blue side is 6. So the ratio of the blue sides is 12 to 6 from large shape to smaller shape. And again, that simplifies down to 2 to 1. For the green side, we have 4 on the larger shape and 2 on the smaller shape. And that again would simplify down to 2 to 1. And lastly, if I look at the yellow side here, we have 18 on the larger shape and the corresponding side on the smaller shape is 9. And again, simplifies down to 2 to 1. So this is what I mean here, here, here and here by corresponding sides are all in the same ratio. All of these are in the ratio 2 to 1. So I can now confidently say that these two shapes are similar because the corresponding angles are equal. In other words, this angle the same as this angle and so on, and the corresponding sides are in the same ratio. So in other words, all of the sides here, corresponding sides are in the ratio 2 to 1. Now, for almost all shapes, we would need to show both of these conditions were true in order to show that they're similar. However, with triangles, triangles are a special case. Triangles, these two properties are mutually dependent, which means I only need to show one of these two conditions, and if I can show that one of these two is true, it means the other one is automatically true. So for triangles, we generally are going to be showing that angles are equal in later problems. But for triangles, we should remember we only need to show one of these, because if one is true, the other is automatically true. In this section, we'll look at being able to find the enlargement or reduction scale factor and using it to find an unknown length in a geometric shape. Before we do that, we need to understand what a scale factor is and what it means for a scale factor to be an enlargement scale factor or a reduction scale factor. So, enlargement scale factor is basically a number which you multiply something by in order to make it bigger. So for instance, if I wanted to take, say for instance, the number 6 and I wanted to make that number bigger, then I could multiply it by an enlargement scale factor. So an enlargement scale factor basically has to be a number greater than 1. If you multiply something by a number greater than 1, for instance, multiply it by 2, it becomes bigger, it becomes 12. If I would take it, for instance, multiply it by, let's say, 5, again, it becomes bigger, it becomes 30. So these two numbers, 2 and 5, would be good examples of enlargement scale factors. Multiplying something by 2 or multiplying something by 5 will both make that number bigger. Again, I'll take the number 6 a couple of times, and say for instance I want to reduce the size of 6, then I need to multiply it by a reduction scale factor. For something to be a reduction scale factor, it needs to be between 0 and 1. If I multiply by a number greater than 1, it's going to make it bigger. If I multiply it by 1 itself, it's going to remain the same. Whereas if I multiply by a number smaller than 1, then that will give me a reduction in size. So, for instance, multiply by half would be a good example of a reduction scale factor. So that would be 3. Or as a decimal, 0.3, for instance, a number again between 0 and 1. That will make a good scale factor. That becomes 1.8. So again, both of these are reduction scale factors. In other words, a half and 0.3, when I multiply by those numbers, it makes the value of the thing I'm multiplying smaller. We'll now get rid of this and look at the problems we're going to be dealing with. We're going to be looking at geometric shapes and trying to find an enlargement or a reduction scale factor to connect the two shapes together. In other words, what would I multiply this length here by in order to get this length here? That would be an enlargement scale factor. Or what would I multiply, say for instance, this length up here by to get its corresponding length down here? And that would be a reduction scale factor. To do that, we have to first of all find the lengths of two corresponding sides which we're given. So in this case, I've got a small rectangle and a big rectangle, and I'm given a side here, A, which corresponds to this side over here, B, on the larger shape. So there are two types of scale factor, remember, enlargement or reduction. Now here I've written out enlargement scale factor for length, and I suppose the important part here is that we are looking in this case for an enlargement scale factor. On the previous slide I showed you that for an enlargement scale factor we need to have a number which is greater than 1. Now when we do these questions we're going to tend to put the two numbers here into a fraction to find our scale factor. If I want that fraction to be greater than 1, then my fraction will need to be top heavy. So to get a top heavy fraction using A and B, remember B is obviously the longer side, so the larger number. If I want my fraction to be top heavy, then I will need it to be B over A. In other words, big over small. We'll then look at reduction scale factor. Now, a reduction scale factor, again from the previous slide, we know that we have to multiply it by a number between 0 and 1. So if we're going to write that, or use these values A and B to write a fraction, we don't want that fraction to be top heavy. Remember, top heavy fractions where the numbers are positive are greater than 1. We want this fraction to be between 0 and 1, so it's going to have to be A over B. In other words, the smaller number over the bigger number. And if we can remember that, then we should be able to easily create the enlargement scale factor or the reduction scale factor we need to go on and solve these problems. Now, you'll notice here that I'm writing out enlargement scale factor in full, and you also might notice that I've put in brackets next to it length. At the moment, length is the only one you'll do, but as we go into the next few lessons, we'll also look at enlargement scale factors for area and enlargement scale factors for volumes. So it's a good habit to get into now to make sure you're saying which enlargement scale factor we're dealing with. So these are lengths we're dealing with in this case. So just putting a little bracket next to enlargement scale factor to say it's a length you're dealing with is a good idea. We'll now go on to the next slide and we'll look at how we can actually use this enlargement scale factor or reduction scale factor to find an unknown length. So in these two examples here, what we're being asked to do is find the unknown value x. It does tell you in the question that the two shapes are similar to each other, so we know they're mathematically similar, so there's a relationship between the sizes here. Now, what I first of all need to do is decide whether the question is asking me to enlarge a value or reduce a value. So first thing I want to do really is start to look at sides which correspond to each other. So on the first question, part A, I would say that this side here, 5, is corresponding to this side here, 8. They're the longer sides on both of those similar rectangles. I would also say that the 3 here corresponds to the x. Now, what we're going to do in this question is we're going to use our scale factor to multiply this 3 to find out the length of x. So I need to decide whether I'm trying to enlarge this 3 or reduce its size. Now, if you look at this side here, this side is longer than this side. So what I'd be looking to do with this 3 is I'm trying to make this 3 bigger to give me this value. So I'm trying to enlarge the 3. So the first step here will be to simply write out enlargement scale factor. And again for length. Now what we want here is we want to have a number which is greater than 1. For it to be an enlargement scale factor, remember it needs to be greater than 1. So I'm going to take the two corresponding sides for which I have values for. So I need to have two values which correspond to each other on different shapes. Okay, so the 5 and the 8 here are perfect for that. And I want it to be an enlargement scale factor. So to make a fraction using the 5 and 8, I have two options. I can either make it 5 over 8 or 8 over 5. Now remember, enlargement scale factors, they need to be greater than 1. So 5 over 8 would be a number less than 1, but 8 over 5 would be top heavy and therefore greater than 1. So it has to be 8 over 5. 8 over 5 is an improper fraction, greater than 1, and therefore it will enlarge any value I multiply by it. The next step is to remind myself that I'm going to try and be enlarging this 3 here by multiplying it by my enlargement scale factor. So this x here will just be 3 multiplied by my enlargement scale factor. So x equals 3 times 8 over 5, which is going to give me 24 over 5. I can type that into my calculator anyway, and that's going to give me 4.8 centimetres. And that will be the length of my value here, x. For the next question, again, I'm going to start by identifying which sides correspond to each other and then using that to decide whether I'm doing an enlargement question or a reduction question. So let's see, this 9 here, the corresponding side on the other shape is going to be the longer side of the other shape, which is going to be the 2 here, and the 6 is in a similar position to this x here, so those two sides correspond to each other. Now what I'm going to be looking at here is, because these two sides correspond to each other, to find x, I'm going to need to multiply this 6 by a scale factor. So I'm going to ask myself, am I trying to reduce this 6, in other words make it smaller to get x, or am I trying to make this 6 bigger? Now because this side is clearly smaller than this side, I'm looking to reduce the size of this 6, so this will be a reduction scale factor, which I'll write over here. So reduction scale factor, and again this is for a length, and here we're going to look at the corresponding sides for which I actually have values. Now these two sides I have values for each, and they do correspond to each other. So I can use the 9 and the 2. And the idea here is to make a fraction with one number at the top, one number at the bottom. Because this is a reduction scale factor, the number I create, or the fraction I create, needs to have a value less than 1. For a fraction to have a value less than 1, it needs to be bottom heavy. So the bigger number needs to go to the bottom and the smaller number needs to go to the top. So my scale factor here will have to be 2 over 9. If I had those the other way around, 9 over 2, the number would be greater than 1, it would become an enlargement scale factor. So what I've got to then do is I've got to take this 6 here and multiply it by my reduction scale factor in order to reduce the 6 to whatever size this is here. So x will simply be equal to 6 multiplied by my reduction scale factor of 2 over 9. Again, that can go straight into your calculator. So 6 multiplied by 2 over 9 is 1.33 recurring. We'll just do that to 2 decimal places there. 1.33 centimetres.